Hello everyone, welcome to Electronically Connected. So in this video, we'll be first discussing what a demultiplexer is, and then we'll be seeing its various types. In this video, we'll be covering what a 1:2 Demux is, and then what a 1:4 demultiplexer is and how it is constructed. So let's get started. So a demultiplexer, as the name suggests, is just the opposite of a mux. If you haven't seen the previous video where I have discussed what a multiplexer is and what its various types, so please click on the link below to see the video. So what a demultiplexer is. A demultiplexer is just the opposite of a mux. So here we have how a demultiplexer works is we have a demultiplexer, we have input, but on the opposite hand we have n number of outputs. But we have only one input. And all of these inputs are just like switches. They are connected to each and every output. The functioning of these switches are controlled by my select lines. So the mechanism behind the demultiplexer is the same as a multiplexer. The properties can be we have only one input. We have 2n number of outputs, and this n, we have n number of select lines. So there we have it. A demultiplexer is just the opposite of a mux, where in the mux we had 2n number of inputs and just one output. But here in a demultiplexer or a demux, we have only one input, and one input is then projected to the number of outputs, and which output it will get projected to will be selected by the select lines. So we can say that as in the multiplexer, a combination of inputs to my select lines will define which output line will have my input. So if my select line is 0 or 1 or 0, 0 or 0, 1, depending on the number of outputs, my select line will select the output in which the input will be projected. Let me explain this better. Let me first explain what are the uses of a demultiplexer. So a demultiplexer, as you had seen, we have one input which goes to n number of outputs, right? So it's basically the input is fed to this input, and we have different outputs at different lines. So that means it can be used for serial to parallel communication. So we can see the input is here serially, and then it gets divided into different outputs. So this goes parallel functioning. So this is also called as series in, parallel out. It is also used for communication purposes, where one particular data is used as an input of serial data, and then it is again decoded and it can be fed from different number of outputs depending on what the select line is. Also, it is used for storing data in a memory. Again, it's the same function where the memory is fed one particular amount of data from the input, and then we have different outputs and it can be accessed through different ways from the memory. There are different types of our demultiplexer as we had it in multiplexer. So our most basic type again is 1:2, 1:4, 1:8, 1:16. Let's see what it means. So we have 2:1 over here, right? And this is 2:2, 2:3, and 2:4. So in this particular case, it means we have one input. This is my input and this is my output. So we have two output and we have one. So we have one select line. Okay. In this situation, we have 4. So we have 4 output and n is equal to 2. So we have 2 select lines. In this situation again, we have 8 outputs and 3 select lines. And in this we have 16 outputs and 4 select lines. But the number of inputs is always 1, and there we have it. So also from this information, what we can see when drawing a circuit diagram for a demultiplexer using a number of AND gates and OR gates. So we can see that the number of outputs are my number of AND gates, okay, and the number of select lines are the number of NOT gates that we use for designing any circuit using an AND gate and a NOT gate. So let's move forward and see how do we design a 1:2 mux and what are the things that we need and the logic behind it. So let's discuss first the 1:2 demultiplexer. So again, we have two output, one input and one select line. So how is the structure going to look like? If you remember, this was how a multiplexer looked like. So if you're doing a complete opposite of a mux, so we have a demultiplexer, which is going to be again a trapezoid, but it's going to be in an opposite direction as a multiplexer. So here we have my input, we have my outputs, and we have my select line. Okay, but right now in our case, we have only two outputs. So we're going to take only two outputs and we have only one select line. So what are my outputs? Y0 and Y1 and my select line S. Now what is the logic behind again this? Y0 is going to be S bar D. Let my input be D. And Y1 is going to be S dot D. Let's see the truth table behind this. So we have my output Y0 and Y1, S, and my input D. So my input is always going to be D. So when my select line is 0, then a D gets projected at Y0 and my Y1 gets 0. Again, when my select line is 1, so this input D gets projected at Y1 and Y0 gets a 0. So how it is happening? Let's say we had this is 0 and 1 for 0 situation. So here it always there is a switch. So if there is a switch which connects, and this is from my input, and this is to Y0 and Y1, and this switch is, both of these switches are connected to my select line. So it operates the switches. As the select line goes 0 or 1, it switches on or off one particular switch, and then thereby my input is present at the output. So if the select line is 0, then it turns this switch on, it connects, and this is stayed disconnected. So the input travels from here to Y0 and hence my input is present at D. But in situations where my input is 1, that means this switch is remained on, this is on, so input gets connected to Y1. Let us now see how the circuit diagram of a demultiplexer is going to look like using the number AND gates and NOT gate. So you remember the number of outputs are my number of AND gates and my number of select lines is my number of NOT gate. So let's draw this. So we have two AND gates. So we're drawing one AND gate and the other AND gate. The output of my AND gate is Y0 and Y1. And here let's draw D. Let's connect my input to both my AND gates. This is my input. Okay, this is D. Now we have a select line S. Let's draw the select line S. The number of NOT gates is just 1 and we need it for Y0. So I'm going to draw a NOT gate and the input of the NOT gate is going from S, and this is going to act as another input to the second AND gate. And there we have it. We have two AND gates and one NOT gate, and this is the total diagram of my demultiplexer using the logic gates. Similarly, we can also design a higher multiplexer. Let's see how to design a 1:4 demultiplexer. So now we're going to dive into 1:4 demultiplexer. Again, 4, that means 2⁻². So we have 4 outputs, 1 input, because it's a demultiplexer, so always 1 input, and we have 2 select lines. So now that means, let's see first the table behind this. So we have S0 and S1, Y0, Y1, Y2, Y3 representing my 4 outputs, and S0, S1 representing the combinations for my select lines. So there are going to be 4 combinations: 0, 0, 0, 1, 1, 0 and 1, 1. So when it's 0, 0, Y0 is going to have my input D and the other outputs are going to get a 0. Similarly at 0, 1, Y1 is going to have my D and the others are going to get a 0. At 1, 0, Y2 is going to get my input D, and at 1, 1, Y3 is going to have my input D, and all the rest of my outputs are going to have a 0. So using this, it's very common to understand how to get the equation. So Y0 is going to have S0 bar, S1 bar and D. Y1 is going to have S0 bar, S1 and D. Remember how this is getting formed? This is from the SOP form, sum of products. So the SOP form, any number in SOP form is 0 is represented with a bar. So it's following that pattern. Again, we have 1, 0. So 1, that means S0. S1 is going to get a bar and D. And Y3 is again S0, S1 dot D. So here we have our equations for my 4 outputs, and we can see we have 4 equations, so 4 AND gates. So we have 4 AND gates and 2 select lines, so we have 2 NOT gates. So let us see how my demultiplexer is going to look like, AND gates and the NOT gates. So let's try and draw 4 AND gates first. So we have the outputs for each of these AND gates are Y0, Y1, Y2 and Y3. Here we're going to have my input, which is connected to all the AND gates. And now we have 2 select lines. We have S0. So S0 is connected as a NOT for Y0. Let's write the equations again first. So now we have 2 NOT gates to be connected. So we have, let's draw a NOT gate for S0. The NOT of S0 is connected to Y0 and Y2. And S0 itself is connected to Y1 and Y3. Now we have another select line, which is S1. We have another NOT gate. Now we can see it is getting satisfied. We have 4 AND gates and 2 NOT gates. So again, the NOT of S1 is connected to Y0, and then we can see to Y1. And then S1 is connected to Y3 and Y2. So there we have it. Here is our diagram for representing a demultiplexer, a 1:4 demultiplexer using AND gates and NOT gates. As we saw in a multiplexer that a bigger multiplexer can be implemented using a smaller multiplexer, so the case holds the same for a demultiplexer as well. We can implement a 1:4 demultiplexer using a 1:2 demultiplexer as well. Let's see how that is done. So a 1:2 demultiplexer again will have 1 input and 2 output. So we're gonna have, this is my 1 demultiplexer. I'm just gonna draw a box for it. You can of course draw a trapezium for it as well. So this is my 1:2 demultiplexer. This is my 1:2 and 1:2. If it is 1:2, that means we have 2 outputs, 2 outputs. And what are these 2 outputs? It is Y0, Y1, Y2 and Y3. So my outputs are ready. Now what about my input? We have only 1 input. This is my input. So from the very first demultiplexer, we'll have 2 outputs, which is going to be fed as the inputs to my other 2 demultiplexers. So we have my inputs ready for these 2 demultiplexer. And what about the select lines? So this first select line, the first block is S0. And the other 2 demultiplexers have a common select line, which is S1. We can even try and test the working of our circuit. So let's take a particular combination. Let's take S0 and S1 as 1, 0. So whenever the select lines are 1, 0, we should get my output at Y2. So let's try and inserting the values. If we insert a value at S0, S0 should be 1. So my input should be projected at the output with select line 1. So this is for select line 0 and select line 1. So my input gets projected at this output. Nothing in this. So now my select line for S1 is 0. And these are my output for 0 and 1. And hence D gets projected at Y2. And there we have it. We can check for another combination. Let's check for another combination. Let's check for 1, 1. So for 1, 1, the output should be present at Y3. So again, S0 is 1. So the output gets projected at this multiplexer. So here we have my input D. And then my select line is 1. If my select line is 1, then my output gets projected at Y3. And there we have it. Just like we have constructed our 1:4 debugs using a 1:2 demultiplexer, in a similar fashion, we can construct a 1:8 or a 1:16 demultiplexer using a smaller demultiplexer as well. So with this, we come to the end of our video. In the next video, I'll be discussing how a decoder and an encoder is used and what is the logic behind its construction. Thank you for watching. Please like, share and subscribe to my channel. Till then, happy learning. See you next time.